Prof, we can't hear you.
The topics for the day. We're going to talk about representing signals, basis-based representations, R bases, Fourier bases, and spectrograms and DCTs for sounds and images. The last topic, Gaussian and Laplacian pyramids, are something we won't cover in class.
Prof, the class is muted. Oh my God.
David, can you hear me? So the class should not be muted. Okay. Guys, can you hear me on Zoom?
Yes.
Okay, so, all right. And so this poem talks about 6 blind men who try to describe an elephant, and each of them describes it differently depending on which part of the elephant they've, oh my good God, looked at. And when we begin representing signals, we are much in the same situation as these 6 blind men. Depending on our perspective, depending on how we view the signal, we're going to come up with very different descriptions. So here are a bunch of pictures. Can you describe them? What do you see? Anybody? Isaiah, what do you see?
Human faces.
Human faces, all right. These things?
Trees.
Trees? Are they all trees?
Some multiple trees. There's also a sky. There's a bird.
There's a bird in one tree.
Imaginary trees.
Some imaginary trees. If you wanted to describe the collection of images, what do you call them? The stuff on top and the ones at the bottom. So, and just to make things more interesting, here's a bigger set of images. How would you describe these? So anytime I ask you to describe these images, when you begin describing them to me, you're trying to give me a content-based description, a semantic description of sorts. And clearly that kind of description is not going to work. When I just give you a collection of faces, you said faces. If I gave you something that looked like trees, you said trees until there was a street going through the trees. And then with this collection, it gets even harder. So clearly, content-based descriptions are infeasible. You're not going to be able to, they don't scale. And at the same time, there's a different way of describing these images, which is 100% non-lossy. If you conveyed this description to the next person, they would be able to reconstruct the signal perfectly. And that is to convey the value, give them the value of every single pixel, saying pixel 1 is 0.25, pixel 2 is 3. But the second kind of description is completely uninformative. It doesn't tell you anything about what's in the data. And so, same thing with sounds. If I look at a sound signal, it looks something like this. It's just a sequence of numbers. When you plot it, it looks like a blob. If I ask you to describe this, how are you going to describe this picture? It's a blob, sounds are blobs, or sounds are numbers. Or if I ask you to describe, a piece of music and you begin telling me 36, 42, 68, and you begin giving me the sample values. Are those going to actually convey the impression of music? Not at all, right? So we have this issue of representation. Representation is description. You need compact representation, but you must describe the most salient characteristics of the data, whatever is most important. Here are 2 images. Are they the same image? Do they represent the same thing?
Yes.
There you go, right? Both of them represent the same concept, the character A. But then if you began comparing them pixel by pixel, how far apart are they? as far apart as they can possibly be. If a white in one pixel is a black in the other pixel, right? So representations must be numeric. You need numeric representations, yet they must convey some information about the content. They must allow identification, comparison, storage, reconstruction, the whole lot. So there are many things that a decent representation must do all at once. And that's a challenge, right? So let's go back to this point. If I asked all of you, without looking at the slide, what is the most common feature of all of these images? Anybody?
Black pixel.
Black pixel, not bad. Anyone else? The rectangles, lovely. Anything else? Pixels, okay. So here's the thing. If I begin describing images in terms of their most salient content, the most common aspect of all of these images is the background. Pretty much every photograph you will ever take is going to be mostly background, right? And what is background? A background is just a uniform shade of some color. So if I want to describe these pictures in terms of just the most salient aspect of the picture, I'm going to describe them as, in terms of the background. What is a background? What is a uniform shade? A uniform shade is just a collection of ones. It's all ones. And so my closest representation for this guy is going to be some constant times a picture of ones. So what would I be doing when I'm describing the data in that manner? This uniform shade, this collection of ones, is essentially a vector in a vector space where it's a vector of all ones. And when I'm describing this image in terms of just this ones, the most salient characteristic, what am I doing? What would I be doing? Projection. I would be projecting the image onto this vector of ones, right? And how would I project this image onto the vector of ones? This image is going to be some vector of pixels. The basis, this uniform shade of ones, I'm going to call it my basis. That's a vector of ones. And I'm approximating my image as some scaling of this basis vector. And so if I were to write the equation down, that's going to be this. I have my image. It's going to be my basis vector times approximated by the basis vector times the weight. And given this, if we saw this in the last class, anytime I write, image approximates b times w, and I've given you b and I've given you I, how do you compute w?
W equals b pseudo inverse I.
So w is going to be b pseudo inverse I. And so your approximation is going to be b times b pseudo inverse I, which I can write as b times b pseudo inverse times I. And this is my projection matrix. It projects the image onto the basis, right? And so I have the projections. I have tried describing two different images. One is the telescope, the other is the face. In both cases, the majority of the image, the most salient characteristic is the uniform shade. But when I project them onto this most salient characteristic, this is what the first image looks like. Does it look like a telescope? And does this look like a face?
No.
Right? But you did capture the most important salient characteristic. So what am I missing? I'm still trying to represent it. When I describe the approximated as this one, what am I missing? Content, the details, right? And so again, we're trying to come up with a content agnostic way of describing things. So what about the features am I missing? When I say everything is a uniform shade, I'm missing change, right? What is change? When the value changes from one pixel to the other. Let's capture the fastest change. What is the fastest possible change? 0 to 1? Every pixel is different from the next pixel. That's the fastest possible change, correct? And so now let me try to describe my image in terms of these two guys. I'm saying my image is some weighted combination of this uniform shade and this really fast change. So if I do that, how would I do that arithmetically? I'm going to have my basis 1 as all ones. Basis 2 is 1 minus 1, 1 minus 1. Every pixel has flipped from the previous one. And so this forms my basis matrix. I'm going to be multiplying it now as W will be a vector because I'm going to be performing a weighted combination of two bases, right? The first call entry of W, this is going to be W1, W2, right? That's what W will be. And this is my approximation to my image. And so I'm expressing every image as a weighted combination of these two bases. And how would I compute the bases again? The weights again? I'm giving you the bases. How would I compute the weights? Can say, yeah? I'll project it onto my bases. And the projection matrix is simply going to be? This is going to be just B times B pseudo inverse is my projection matrix, right? And so once I do that, I get my weights, and then I'm going to be expressing every image as W1 times B1 plus W2 times B2. The bases are constant. The difference between the images is the weights with which they're combined. But so I've expressed my telescope as some W1 times the uniform plus W2 times the really fast change, the fastest change you can find. And that approximation looks like this figure here. Does it look like the telescope? So what am I missing? More detail. That's the fastest detail you can get, right? Things that change from one pixel to the other.
Some things change slower than that.
Some things change slower than that, right? So I can keep adding more of these things that look like checkerboards. These are my checkerboard bases, what I call my Haar bases. So the first image says across the image changes from white, changes once from white to black. Vertically, it changes once from black to white to black horizontally as well. And so that gives me this as my basis. Then here is a basis which changes once from top to bottom. But going left to right, it cycles through black and white 8 times. Here's something that cycles through black and white 4 times or twice vertically, but 6 times horizontally. So I can keep adding more and more bases which capture faster and faster rates of change. And what I would be doing is trying to explain my image in terms of these bases. So what am I doing? I'm projecting the image on the bases. And the math behind it is that I just write all the bases out as a column vector, as a matrix. And then the weights are a column vector that the basis matrix will multiply to generate my data. And I have to estimate the weights, which best explain the data. That's obtained by projection, also computed using a pseudo inverse. Right? So the projection, it projects it on the bases. The pseudo inverse gives you the weights. Easy. And so I can keep adding bases. And as I keep adding bases, the image begins to get more and more detailed. By the time I get to 625 bases, it begins to have some structure. How many bases do you think I would have to add before it actually looks exactly like the telescope?
As many bases as the image pixel number.
As many bases as the number of pixels in the image. Adding more than that is not really going to help, right? And so that's what I would get. So here's my first pull. Did that make sense to everybody? All of you? That makes sense? Okay. Anybody want to answer this question? Is the first statement true?
Yes.
Second, third. Why is the third not true?
Linearly dependent. Yeah, some basis. Linearly dependent.
Mhm.
You're limited by the fastest change.
So you're limited. You cannot have more bases than the number of pixels in your image. And so the first two statements are true and the third one is false, right? So what kind of representation was this? This was actually a better representation than content-based representation. This was better than saying, it's a tree or it's a face, because that's an unlimited descriptor. It was also better than saying the first pixel was 0.2 and the second pixel was 0.3, because it actually captured some notion of structure. It says the slowest change has a weight of 0, the next slowest change horizontally has a weight of 0.1, the next slowest change vertically has a weight of 0.3. It represented your data in terms of structural components, but there's something special about these structural components. I'm using the same structural components regardless of which data I'm trying to represent. So these are standard representations. The checkerboards are the same regardless of the picture I'm trying to describe. And every single image is simply being characterized as a weighted combination of these checkerboards. And once we have decided on the checkerboards, you and I don't have to tell you what these bases are. I can just convey the weights to you. And when I convey the weights to you, that is sufficient for you to reconstruct the image. But those weights also carry some information about the structure of the data. So they are a representation in a structural sense. Does that make sense? Right. Okay. So, and unless I have a complete set of checkerboards, I may not be able to reconstruct the image fully, but I can reconstruct the totality of it to some approximation quite well, as I did in this case, right? So what about sounds? Sounds are these waveforms like the one I have on the top in the picture. And the square wave equivalence for audio signals is going to be a one-dimensional square wave, as we just saw. And then once again, over here, if I want to represent, I can use the same trick as before. My sound signal would become a vector. My bases can be laid out as vectors in my basis matrix. And then I can use the same arithmetic that I just did to estimate the weights with which these bases must be combined. The pseudo inverse of b times the signal will give me the weights with which the bases must be combined to reconstruct the signal. Now, so you get an idea. Now, the general philosophy of this kind of representation is to identify a set of standard structures like checkerboards. These are what we're going to call our bases. There's a mathematical notion of a basis in a vector space. From a signal perspective, these are the standard structures that we can use to compose signals. And we're going to express the data as a weighted combination of these bases. So x equals w1, b1 plus w2, b2 plus w3, b3. You're just expressing x as a weighted combination of the bases. And our job now is to choose the weights, w1, w2, w3, and so on, such that this weighted combination is as close as possible to the data that you're trying to represent. And when you do so, if your set of bases is not complete, then more often than not, there is some aspect of the signal that you're not fully characterizing. And there will be an error between what you reconstruct and the original signal. Even if you have the complete set of bases, the idea is to estimate these weights such that the squared error between the original data and the weighted combination of the bases is minimized. And that's in fact what projection does. And once this is done, the weights that you compute fully specify the data. If you and I have agreed upon the bases, if I just give you the weights, you can reconstruct the data. So far so good. We've defined the notion of basis-based reconstruction, but what are good bases? Now, there are some principles you can come up with on your own. Yes.
So when you say that if you just have the weights How do you reconstruct it with just the weights? You need the basis as well.
Yeah, so long as we've agreed upon the bases,
Okay.
right?
The basis would be the
These are standard bases, right? So long as you and I know what the bases are, you just need to know the weights. And now the weights represent the data, right? So you want the bases to be non-redundant. If I gave you, for example, a uniform shade as my first basis, and you try to reconstruct an image, and you found you could do, you did, when you did so, you got some gross errors. And you come back to me and say, oh, I've got an approximation, but it's really bad. Can you give me another basis? If I gave you back the same uniform shade, are you getting anything new? It's completely useless. What do you want this new basis to be? You want it to capture structure that is absolutely not captured by the prior basis. Every new basis that you include to the set must capture information not already represented by the other basis. So in a mathematical sense, what would this mean? I want my basis to be completely unrepresentable by the other basis. What would that mean? Orthogonal, right? They must be at 90 degrees to one another. So every time I give you a new basis, the new basis is at 90 degrees to the previous one. Or the inner product between any two bases must be 0 if the two bases are not the same. But then you have another property. I want to capture maximum information using the smallest number of bases, the ability to compact. If all you had, one of the things we used to do back in the day is we have a secretary called Catherine, and anybody who went anywhere would send her a picture postcard. It was a running gag. Rio de Janeiro by night, Paris by night, Berlin by night, Antarctica by night, Bombay by night. It was just a black patch. And so that was all it was, right? The moment you knew that Catherine had got a picture postcard, you knew what it looked like, right? Do I need it to convey any additional information about it? No. Sometimes, if you got to really brightly lit places, then the picture postcard would have a shade of gray rather than black. Someone sent something from the Arctic Circle, and it was gray. So the only bit of information you needed was the shade. The basis was understood. Now, this is a very compact representation. All you needed was one number, and you could reconstruct the picture postcard exactly. This is what you want in a general set of bases. You want the bases to be such that you want to be able to convey as much information about your data as possible using the smallest set of numbers. You want the representation to be compact. Or you must be able to represent most of X with the fewest bases. And you can see, if I'm living in d-dimensional space, you never need more than d bases for this. Now, you might get away with fewer in some cases. Now, so there's an interesting property about orthogonal bases, and that's this one. There's always missing the duster. Yeah. Suppose I have a matrix. First, some properties of matrices. If I have a matrix of size m cross n, what is the size of the pseudo-inverse? Anybody? Can you say it aloud, please, Anka? N cross m. The size of the pseudo-inverse is always going to be the transpose. N cross m. So now if I have a column vector, like so, what is the size of the pseudo-inverse of this column vector?
One cross n.
So if this is n cross 1, the size of the pseudo-inverse is going to be 1 cross n. So if this is x, x plus is going to be 1 cross n, okay? Now, assume that this vector has length 1. Meaning, if I take the squared sum of all of the components of the vector, it has length 1. right? Then what exactly is this? What is the property of the pseudo inverse in this case? What is x plus x going to be in this case? What is x plus x going to be? X plus is the pseudo inverse of x. It's going to be 1, correct? Everybody agree with me? So is it a scalar or a vector? Scalar. What is x plus going to be? Remember, b is the length 1. What is x plus? Lucy, what's x plus? What's the pseudo inverse of x? X is a column vector of length 1. And yes, which vector? Come on, guys.
Total units.
Mhm.
Total units.
It's a unit vector, but which vector is it?
X transpose.
It's just going to be x transpose, right? So here, when I'm telling you that the length of x is 1, if the length of x is 1, then what I'm really telling you is that the norm of x squared is 1, which implies that x transpose x is 1. So the pseudo inverse of x is its own transpose, right? And if x is not length 1, then what is the pseudo inverse of x? What is it going to be? Yeah,
Scalar times itself.
it's going to be a scalar. And what will that scalar be? X plus is going to be 1 over length of x times x transpose. That way, when you multiply the two, it's going to become a 1, correct? So everybody good with me so far? Now, what is x plus in this case? What is x plus?
Matrix, right?
It is a matrix. Which matrix is that?
N by N matrix.
It's an n by n matrix which projects it onto that one vector. Right? Everybody with me here? Okay. You guys, everyone with me? Yes, okay. Now, let me give you two vectors, x1 and x2, and both are length 1. If both are length 1, that means that the squared norm of each of them is 1. I'm also telling you that they're orthogonal to one another. So this means that xi transpose xj equals 0 if I not equal to j and 1 otherwise, right? So from this, if I compose a vector, if I just put these two vectors into a matrix, this is x1, x2, I'll call this x. What is x transpose x in this case? The two vectors are orthogonal and they're length 1. What is x transpose x? It's going to be, the x transpose x is going to be, norm x1 squared, norm x2 squared, and then x1 dot x2, x2 dot x1, which is simply going to be the identity matrix, right? Everybody with me? So what is the transpose, what is the pseudo inverse of x?
Transpose.
The pseudo inverse of x when x is an orthogonal matrix. But do you guys mind shutting your laptops, please? Yeah, sorry, you too. Thank you. Okay. So when x is a matrix of orthogonal vectors, then the pseudo inverse of x is just its own transpose. This comes up with this ends up with having a very beautiful outcome, which is this. If I have a basis matrix X comprising B1 and B2, and I want to compute the vectors, say W1, W2, such that this composes a vector X. How do I compute W?
Just B transpose X.
This is the pseudo inverse. So this is going to be B transpose X. And what is W1?
B1 transpose X.
W1 equals B1 transpose X. W2 equals B2 transpose X. So the beauty of this orthogonal set of matrices, vectors, is that when I want to compute the projection onto any one vector, because they are orthogonal, I can ignore all the rest of them. I can do this one at a time. This only happens when the basis vectors are orthogonal, right? Okay. And so this happens regardless of, and if the vectors are not orthogonal, but if they're not unit length, and they're still orthogonal, you just have to normalize by the length. But the point here is that this does not depend on whether the basis matrix is square or not. In every case, if I have a basis matrix comprising orthogonal vectors of length 1, then the pseudo inverse of the matrix is just its own transpose, right? Here's a it's on the slide. Okay. Can anybody answer the first question?
True, true,
Okay. The first statement and the second question.
true, true.
And the second statement? Right. Okay. The pseudo inverse consists of an orthonormal matrix consisting of orthogonal unit vectors as its own transpose. If all the bases are orthogonal to one another, the weights of these bases to compose a vector can be determined individually for each of the bases. These two are true, right? This cannot be done if they are not orthogonal. So now, having said all of that, what are good bases? Checkerboards are great bases. Every checkerboard is orthogonal to every other checkerboard. If you don't believe me, just think of whites as ones and blacks as minus ones. What is the inner product between a checkerboard which is all one and any other checkerboard? That's 0, because every white is cancelled by the corresponding black, right? If I take two checkerboards which are different frequencies, different number of cycles, if I lay them on top of the other, the number of locations where the two checkerboards match is going to be exactly the same as the number of locations where the two checkerboards do not match. So if I take a product, component-wise product, and sum it up, the matches will cancel out the mismatches. You're going to get a 0. So checkerboards are orthogonal, which means that I can determine the contribution of these individual checkerboards just using an inner product or a normalized inner product, right? But then checkerboards are horrible bases for other reasons. If I have a sinusoid is a smooth curve. A checkerboard is all corners. Can I ever express that sinusoid as a weighted sum of these checkerboards? I'm only going to get corners, right? So what would be a good set of bases to express a sinusoid? A sinusoid itself, right? So that leads us to Fourier bases. Sinusoids are great bases. If I take two sinusoids of different frequencies, they're going to be orthogonal to one another. The inner product is 0. They can represent rounded shapes nicely. Unfortunately, they cannot represent sharp corners, but we've never ever encountered really sharp corners. It's not a big deal. And they follow the same format as the checkerboard. You have the 0 frequency sinusoid, just a DC. Then a frequency 1, which is going to cycle once over the duration of the signal. Frequency 2, it's going to cycle twice over the duration of the signal, and so on. And so I can keep going on until I get to a certain number of cycles over the sinusoid, and we'll see what. But for the kth sinusoid, if the signal length is n, I've plotted it continuously, but these are just a discrete sequence of numbers, right? So the kth sinusoid is simply given by 2 pi k n over cap n. Cap n is the length. And what this means is that it's going through k cycles over length n, as you can see here. This one?
The one with the checkerboard. Sorry, can't I just make the checkerboard like infinitely small and get a equal approximately that?
You cannot. You're always going to have corners, no matter how small you make it. It's discontinuous. You cannot approximate a continuous function with a discontinuous function, period, right? So you cannot accurately represent, okay? And so, but then how many sinusoids can you get? If I have a signal of length n, I can get a DC. I can get a sinusoid with 1 cycle, with 2 cycles, with 3 cycles. What is the maximum number of cycles I can get? So if in this case, if I have a length L, I can get up to L over 2 cycles. If I try to get more than L over 2 cycles, it's going to end up looking over like a sinusoid that has fewer than L over 2 cycles. We saw this in the first lecture. It ends up with aliasing. Because when I get L samples over here, the blue lines show the L samples. And here L is 20. The red sinusoid has 9 cycles in 20 samples. The green sinusoid has 11 cycles in 20 samples. At those 20 samples, are those 2 sinusoids different? Yes or no? Can I hear a no? Right? Because they intersect 20 times. And the measurements we take are going to be at exactly those 20 points. These 20 intersections are uniformly spaced. So in general, if I have a sequence of length L, I cannot get more than L over 2 cycles. If I try to go over L over 2 cycles, I just end up recreating a sinusoid with fewer cycles. Okay. And so how are we going to represent signals in terms of sinusoids? I'd have my signal here. I just pack up my sinusoids as a basis matrix, and then the usual trick. The sinusoids are orthogonal, just so long as I make sure that the sinusoids are all normalized, so they have length 1. Just the transpose of the basis matrix times my signal is going to give me my weights. No big deal, right? But then, so here's what it's going to look like. So this is a sinusoid of, for a length L signal, this is the sinusoid of frequency 0. Sine of 2 pi 0 times n over L, right? The next column is going to be a sinusoid of length 1. The next would be a sinusoid of frequency 1. The next one would be a sinusoid of frequency 2 cycles over the duration of the signal. And so the kth column is going to be 2 pi k n over L, where n is the sample index and k is the column index. Easy enough. And we can compute our representation in terms of sinusoids. And what exactly are we doing when I'm beginning to represent sinusoids into signals in terms of sinusoids? Now, firstly, sinusoids are orthogonal to each other, as we just saw. So when I have a signal of this kind, like the red line, I can find the contribution of each sinusoid independently without considering the other sinusoids. And in order to find the contribution of any given sinusoid, I have the sinusoid, and I'm going to try scaling it to different amplitudes until I find an amplitude where the total square difference between my signal and the scaled sinusoid is minimum. And that is going to be the weight of my sinusoid. So we even have a very nice interpretation of what it means to find the weight for the individual sinusoids. But sinusoids by themselves have a problem. A sinusoid, what is the first value of a sinusoid? What's sine 0? 0. If I have a signal whose first value is not 0, can I ever express that as a weighted combination of sinusoids? So it's not precise, right? What would I need for a signal where the first sample is not 0? Cosines. But can I ever represent a signal whose first sample is 0 as a sum of cosines? Not unless the entire signal is 0. So neither sinusoids nor cosines by themselves are sufficient. So we need both, right? And so we need phase. It's not enough to have a sinusoid. We need to be able to let the sinusoid slide left to right. We know that we need sinusoids up to frequency L/2 cycles, but it's not sufficient to say I'm going to use the sinusoid. I'm also going to have to say, how much do I shift the sinusoid by? And so the actual signal is going to be represented as a weighted sum of sinusoids, where each sinusoid has its own starting point. You're sliding left to right. The sinusoids are still orthogonal. You can still find the contributions of the individual sinusoids by themselves, but now they have a phase. So what would we be doing in this case? You're going to do a least square splitting. You'll be trying, for each sinusoid, you'll be trying to determine two things. One is the amplitude, and the second is how much do I shift it left to right, so that the total squared error between the sinusoid and the signal is minimized. So both the phase and the amplitude. Can I write this as a linear algebraic equation? Yes or no? Let me write the equation out, right? So this is what it looks like. The first matrix is my basis matrix. Each column is one sinusoid. Each sinusoid has a amplitude and a phase, right? Are the amplitudes part of the basis matrix? Where are the amplitudes? The W, right? And I have the signal to the right. Can I solve for W's and phi's using algebra? Yes or no?
Yeah.
Why not?
Phi's and the W's are unknown.
And the phi's are unknown, but it's not just that. The bases are unspecified. The bases themselves have an unknown, which is phi. And so once you have that, then there's really no clean decomposition. This is not a standard linear decomposition that you can use to find both the bases and the phase for the bases and the amplitude. So now we're going to have to, what this means is that I'm going to have to somehow get a hold of these phase, and for this to work, and for this to work in an algebraic manner, I need to be able to pull the phase out to the right-hand side, to the W column, so that the basis is cleanly specified. And how do I do that? This is where math comes in. Everybody's familiar with complex numbers, right? What is Euler's formula for e raised to ix? Cos x plus I sine x, right? So now I can begin writing complex exponentials. If I write e raised to j times frequency times n, that's going to be cosine of frequency times n plus j times sine frequency of n, frequency times n, where j is the square root of 1. So this complex exponential has a real component and an imaginary component. The real component is shown in blue. That's a cosine. And the imaginary component is shown in red. It's vertical. It's the sine component. So the nice thing about complex exponentials is that now I can include a phase. How so? The complex exponential gets both the sine and the cosine. So I've got the sine aspect, sinusoidal aspect of the basis. But then once I include a phase, that's e raised to j times frequency times n plus phi. And the phi simply comes out as a separate term, e raised to j times frequency n times e raised to j phi. And so what this means, and of course, when you decompose it, it's a cosine with a phase and a sine with a phase. But the beauty of it lies in the fact that you want to remain in complex space. And now I'm going to try to express my signal as a weighted sum of complex exponentials. And when I do so, here's what we find. First, complex exponentials are extremely well behaved. Like sinusoids, a complex exponential of one frequency can never express a complex exponential of a second frequency. They are orthogonal to one another. They can represent smooth transitions. Bonus, they're complex. They can even represent complex data, but here's the lovely bit. They can model real data. E raised to jx plus e raised to minus jx ends up being real. And you can just write it out. It just becomes 2 times cos x, right? So they can model real data. And now, here's how the decomposition is going to happen. B basis matrix now is going to have complex exponentials rather than sinusoids. And each of these complex exponentials is going to be multiplied by a weight, which took to give me my signal. But it turns out that I can get fully L complex exponentials in L samples, rather than just L over 2, because for the first L over 2 complex exponentials, the sine and cosine will have the same, the cosine and sine will have the same sign. And then for the remaining, you get back the earlier frequencies, but the phase relationship between them is inverted. It's going to be cos plus sine for the first half, cos minus sine for the next second half, right? But that's besides the point. So here's what happens. Now I can actually write the basis matrix like so, where every column is a complex exponential of one frequency. Now, in principle, I want to actually shift the sinusoids left and right, correct? That means I want to multiply the I want to have the complex exponentials have a phase. But the phase ended up being a multiplicative term for my complex exponential over here. It just came out. So when I write W times e raised to this guy, that simply becomes e raised to j frequency n times W times exponential of j phi. So what happened? I can group W and e raised to j phi, and now the phase moved into the weight. And so by writing things as complex exponentials, I ended up with this beautiful math where I moved the phase into the term that comes out to the right. And now it's linear algebraic all over again. I can just use algebra. So this is one of the reasons we like to work with complex exponential bases. We like algebra. Things are simple. We know how to deal with these things. And because the phase is a multiplicative term, that factors into the capital S, uppercase S. And this is what the whole thing looks like. Now, the key thing to observe over here is that there are, for a signal of length L, you're going to get L unique complex bases. The matrix is square, the basis matrix is square. When I was using sinusoids, I got only L over 2 of those. After that, they began repeating, right? But when I'm using complex exponentials, I'm going to get L of these guys. And so here is the next problem. Any questions so far? Questions? Questions? Okay, all right. Puru, you want to answer the first question?
True and true. First two are true.
First two are true. And forget your name. Yeah, your buddy, of course, right, buddy? So can you answer the second question? L, right? We just said there are L unique complex exponentials, and they enable us to use linear algebraic math to express signals as linear combinations of phase shifted sinusoids. We managed to get phase into the weight outside. And they can indeed be combined to construct purely real signals. Questions? Any questions? So the fun part is over, then it gets pretty complicated, right? So complex exponentials can be used to construct real signals. That's because they have conjugate symmetry. If I have e raised to j pi times L over 2 minus x n over L, and L over 2 plus x times n over L, that just ends up being a cosine. It's real, right? And so, and complex exponentials with frequencies that are equally spaced from L over 2 are complex conjugates, meaning unlike the sinusoids, in the case of the sinusoid, the red and the green sinusoid gave you the same samples. So you can't distinguish between them. If I multiply the red signal by weight W1, it's the equivalent of multiplying the green signal sinusoid by weight minus W1, right? But in the case of the complex exponential, the two are different because each of them comes with a cosine. So one of them is going to be cosine of argument plus j sine argument. The other is going to be cosine of argument minus j sine of argument. So you have to, that's why these things become distinct. And so when you want to construct a real signal, you're going to use, again, I'm just sort of glossing over this, but there's something that there's a key point over here that we'll get to it. That's all you need to remember. Since the frequency L over 2 minus x is a complex conjugate of frequency L over 2 plus x, if I multiply this complex exponential by a and this complex exponential by the conjugate of a, the two terms that I'm summing are complex conjugates. So what will the result be? It's going to be real, right? So what this means is that anytime I'm trying to explain a real signal using complex exponentials, I'm going to find that the weights on either side of L over 2 that are equally far apart are going to be complex conjugates of one another. So which means I just need the first L over 2 weights because the rest of them are just their complex conjugates. They're implicit, okay? Another thing is that if you look at the algebraic formulation, this is just the basis, but the basis matrix is complex. Now the length, the individual vectors there are not length 1, but I can normalize them to length 1. If I normalize them to length 1, the columns are also orthogonal to one another, right? So what would the pseudo inverse of this matrix be? Just the transpose? It's complex. So it's going to be the complex conjugate transpose, right? It's going to be, so if I were to, I'm just writing this, I've normalized these bases to length 1, right? So the columns now, I'm doing something that I'm writing as W L over 2, W00, this W01 with subscript L is e raised to 2 pi 0 n over L. This first number represents K. The second number represents N. The subscript represents the denominator in the complex exponential. So if I write it like so, this is just a simplified notation, then my basis matrix is this W matrix times my weights, which give me my signal. And the property over here is that where, for real orthonormal matrix, we saw XX transpose equals identity. X transpose X shall be, right? But only if all the entries are real. For complex matrices, you want to look at the Hermitian. The Hermitian is the complex conjugate of the transpose of the matrix. So in that case, you're going to find X Hermitian equals X Hermitian X equals I. And so in this specific case, what does that mean? How do you find the complex conjugate of a complex number? If I have e raised to j theta, what is its complex conjugate? E raised to minus j theta, right? So if this is W, which is simply e raised to j2 pi k n over L, what is its pseudo inverse? It's going to be the transpose complex conjugated, right? So you're just so when you're transposing it, you're just going to be flipping these two indices and adding a minus. That's all you're doing, right? So here, this matrix was e raised to j2 pi k n over L. This is going to be e raised to minus j2 pi n k over L rather than kn over L. That's it. And so this matrix over here is the Hermitian of your basis matrix. This is also called your Fourier matrix. And this, to compute the weights S, this was your basis matrix of complex exponentials. You multiplied them with S to construct the signals. So what are these weights? The signals are just the conjugate of your basis matrix, the Hermitian of your basis matrix times the signal. And this Hermitian, this guy here is your Fourier matrix. It's kind this entire transform. This for the mechanism of deriving these weights with which you combine complex exponentials, they're called the Fourier transform of the signal. And the process of deriving these weights is also called a Fourier transform. So if you ever wondered where, in fact, this is called the discrete Fourier transform because you're working off sequences of numbers. And so if you ever wondered where discrete Fourier transforms came from and where the formula came from, you're just representing signals as weighted sums of complex exponentials. And the Fourier matrix, which is the transform itself, is given by this little matrix operation over here. And this brown matrix is the Fourier matrix, which is the Hermitian of your basis matrix. And if somebody gave you just the weights, the S's, and asked you to compute the signal right back, all you have to do is to multiply this guy by the Hermitian of this matrix, and you get the signal right back. Right? So multiplying the Fourier transform by the Hermitian of the Fourier matrix, which is the transpose conjugate, will give you the signal right back. So this is the forward and the inverse discrete Fourier transform. Now, I'm not going through the standard manner of defining Fourier transforms. For me, it's all linear algebra. That makes sense to everybody? Right? And so what does this Fourier matrix look like? When I plot it, I can plot the real and imaginary parts, and what is it you observe? Looks very symmetric, doesn't it? It's symmetric, and it's got almost fractal symmetry. Every subpart of it is symmetric. And so how many of you have heard the term fast Fourier transform? The fast Fourier transform, pretty much all of you, right? What do you think the fast Fourier transform is doing?
Using the symmetric property.
It's just using the symmetry of these Fourier matrices to make the computation much, much faster. The actual transform itself is the discrete Fourier transform. The fast Fourier transform is just using this to make the computation more efficient, the matrix computation more efficient. Any questions? Questions? No. Okay. So the outcome of the transformation of the Fourier matrix is the discrete Fourier transform. The fast Fourier transform is an algorithm that takes advantage of the symmetry to perform the masked matrix multiplication really fast. So the FFT computes the DFT, in case you've ever wondered. It's much faster if the length of the signal can be expressed as a power of 2. Now, that's all about one-dimensional signals. What about images? Now, the complex exponential has, in the case of images, you have a frequency, you can still use the same property. But images are two-dimensional signals. So you have a frequency along the x-axis, and you have a frequency along the y-axis, and the two are entirely different. And so you can use the same thing, except now you would have a two-dimensional discrete Fourier transform, and you can represent your images in much the same manner. And so here is what the real components of the various Fourier bases for images looks like. For one-dimensional signals, they were just sinusoids. And if I were to plot the real component of the bases, they would just be cosines. For the two-dimensional Fourier transform, discrete Fourier transform, this is what the real component of the bases look like. And if you perform the discrete cosine transform of this guy, you're just going to overlay each of the individual bases on top of it and compute the inner product. So this guy here is the discrete Fourier transform. This is the lowest frequency. This is the horizontal frequency. This is the vertical frequency. The two are different. And what do we find? Most of the energy in the signal is in the lowest frequency. This kind of aligns with the idea that most of any picture is just basically background. And there's really very little going on at the highest frequencies. Make sense to everybody? Good. Okay. So much. And DFT has properties, which just take a look at the slides. It has some, with the properties that the DFT of A plus DFT of B simply the DFT of A plus, the DFT of A plus B is the DFT of A plus the DFT of B. We use it all over the place. We use a horrible approximation. You'll also use it in your homework, where we say that the DFT is going to give you a complex number. The weights are going to be complex. But we often assume that the magnitude of the DFT of A plus B is the magnitude of the DFT of A plus the magnitude of DFT of B. Clearly, the magnitude of the sum of two complex numbers is not the sum of their magnitudes. So this is a terrible, terrible thing to be doing. A mathematician would beat us with a whip or something, but we are engineers, we just do this. Now, so we're assuming everything is in terms of complex numbers. But our data are all real, right? And so look at this guy. Suppose I have a symmetric signal of this kind. If I have a symmetric signal of this kind, then the points on either side of the center point are exactly the same. Let's also assume that the signal is entirely real. So when the signal is entirely real and symmetric, you can sort of easily work out the arithmetic and show that the Fourier transform is also going to be real and symmetric, meaning the S values that you saw. We know that if the signal is real, the S values have conjugate symmetry. The upper half is the same as the conjugate of the lower half. But if the signal is also symmetric, you're going to get, it's not only going to be conjugate symmetric, it's also going to be real. So when the signal is real and symmetric, the Fourier transform is going to be real and symmetric. It's a property, easily proved, but you're going to have to take my word for it. And we will use this. So if I have a signal, now the problem with working with Fourier transforms is that you're decomposing signals in terms of frequencies, but the weights we get are complex. And nobody wants to work with complex numbers. How many of you are happier working with complex numbers than real numbers? Anybody? Isaiah. So you will work with Fourier transforms, but what about the rest of you guys? Do you prefer complex numbers to real numbers? I don't know a person yet to date who does other than this guy. So, and so we're going to try to make things real. Now I know that if I have a real signal of this kind, the Fourier transform is complex. But I know that if the real signal is symmetric, the Fourier transform is real. So what can I do? I can make it symmetric by simply reflecting this guy around the center and attaching the two. And now I have a symmetric signal. I can compute the Fourier transform of this one. It's guaranteed real. It turns out that this is what is called the discrete cosine transform because only the cosine terms remain in the bases. And the Fourier transform is also going to be symmetric, which means I can throw away the lower half. And I get a representation that's perfectly real and fully characterizes the signal in terms of its frequencies. Now, we don't like to do this with one-dimensional signals, but with images, we do it a whole lot. If somebody gave me a picture of this kind, the first thing I would do is to reflect it horizontally, reflect the whole thing vertically. And now I have a two-dimensional signal, which is symmetric. And now I can perform a two-dimensional Fourier transform. It's going to be real and symmetric. I won't bother with the two-dimensional Fourier transform. Instead, I just stay with the real terms, and that's going to give me my discrete cosine transform. And so anytime we work with images, we generally work with discrete cosine transforms. And if you wonder what a DCT is, the DCT is just a Fourier transform of a symmetrified signal, where you take the signal, reflect it, and make it symmetric, right? And as it turns out, you don't need to explicitly do it. You can just do it implicitly by constructing your basis matrix using just cosines, and the whole thing just works. And you're going to get L terms, which represent the Fourier decomposition of the symmetrified signal. Right? So, questions? Yeah.
Why is it not performed on 1D signals?
You could. Yeah. So it turns out that in the case of the 1D signal, there's a little bit of, we generally think of sounds. And when I'm thinking of sounds, unlike in the case of images, in sounds, the only thing that matter is continuity. And so there's my chalk. So let's say I have a signal of this kind. And if I can represent it as the sum of this sinusoid and this sinusoid and this sinusoid and so on, weighted sum of these sinusoids. And if I slide one of these guys a little bit, if I add them up, will I get back the original signal? No, because one of them has been slid, but they will sound exactly the same. So our ear has this insensitivity to phase shift in the individual components of a sound signal, which means that we don't have to worry about the phase as far as processing is concerned. So for sounds, we just work with Fourier transforms. It's simple. But for images, if I shifted one component by a bit, it's going to be completely different. It's going to be something destroyed. So we work with discrete cosine transforms. You don't want to work with complex stuff, right? Any questions? So, the most common coding of images in the world is the JPEG coding. And that uses the discrete cosine transform. You just take the image, you chop it up into little portions of 8 cross 8. Then you perform the discrete cosine of each 8 cross 8 element. That's going to give you a DCT of this kind. And then you can quantize or throw away many of these terms. And you can still go back, and if you throw away all the really low value terms, you can still go back and reconstruct that 8 cross 8 segment pretty much exactly. And that means you can throw away much of the image and still get something that can be used to reconstruct the image pretty much very close to what you began with. And this is what JPEG compression does. So these were all deterministic representations of audio time series and image data. And there are various engineering considerations that we take that we must take into consideration. Direct computation of the Fourier transform can result in poor representations. You can get boundary effects. So you'd like to taper the signals off at the boundaries. The size of the signal can introduce inefficiency. If you want to compute a fast Fourier transform, you want the signal length to be a power of 2. So we like to pad with zeros. There are lots of things that we do. But instead of getting into that, I'm going to talk about something else slightly more interesting, how we represent audio signals. There's nothing magical about audio signals, but I'm using audio signals as an example over here. The same characterization can be used for any kind of one-dimensional time series data. So for this, how many of you are familiar with tuning forks? You, okay. Suppose I struck a 3 kilohertz tuning fork. What would it do?
Would ring out and produce 3 kilohertz.
It would ring out and produce 3 kilohertz. Now, suppose I stuck a 3 kilohertz tone or tuning fork over here, and I played a 3 kilohertz tone at it. What would happen to it? It would resonate. And if I increase the amplitude of the tone, what would happen? It would resonate harder. So now just imagine that you have a friend sitting on the other end of campus, and he has a tuning fork, and so do you, at 3 kilohertz. And you stick it over here, and to your tuning fork, you attach a sensor, which senses how energetically it vibrates. And you converted this to an electrical signal. And this is being communicated over a wire to your friend at the other end of campus or maybe in China. And he has a tuning fork where he uses the signal coming down the wire to excite a tuning fork to vibrate in proportion to the signal that comes down. Now, if I play a 3 kilohertz tone over here, what will he hear? 3 kilohertz tone. If I increase the volume over here, what will happen on his end? Would it increase or decrease or stay the same? Increase. Okay, so right now, that was just with one tuning fork. Now, suppose I give you 2 tuning forks. One of them at 1000 hertz, the other of 3000 hertz. And you do the same thing. You stick 1000 hertz tuning fork here, one 3000 hertz tuning fork, and you stick wires to both of them, and both of them communicate to your friend on the other end of the planet. And he excites the 3000 hertz tuning fork with the signal coming down the 3000 hertz wire. and the 1000 hertz tuning fork with the signal coming down the 1000 hertz wire. And then in this room, I keep playing an alternate of 1000 and 3000 hertz tones. What would he hear?
An alternate 1000.
He's going to hear an alternate of 1000 and 3000 hertz. I play you a mix of 1000 and 3000 hertz tones, which is, where the 3000 hertz tone plays, 5 times as energetically as the 1000 hertz. What would he hear? He's going to hear the same mix, where the 3000 hertz is going to be 5 times as energetic as the 1000 hertz. You agree? Right? Now, suppose I have an entire bank of tuning forks in my world. 5, 10, 15, 20, 25, 30, 35, all the way up to 10,000 hertz. And I've conveyed their vibrations to my friend in China. And then I play Mozart's 40th over here. What's he going to hear?
Pretty good approximation.
A pretty good approximation to Mozart's 40th, right? Where does the information lie? It's in the wires that go from here to his place. If someone were to slice all the wires, record the signals, and just store those numbers in a computer, and much later, 6 years later, they use those same numbers to excite a new set of wires which excite tuning forks, what would he hear? The pretty good approximation to the Mozart's 40th. That matrix of numbers is what we call a spectrogram. So if you think of what a Fourier transform does, a Fourier transform is really a bank of tuning forks. Each of your sinusoids is a tuning fork. And so when you're trying to find the amplitude of each of your sinusoids or your complex exponentials, you're finding the amplitude with which that particular tuning fork vibrates. And so we use this principle to compute spectrograms, which are a representation of audio signals. Let's say I have an audio signal of this kind. Now, so when I play music here and I convey it to my room, is the signal in all the wires constant all the time? As any particular frequency goes up and down over here, that signal is going to go up and down, right? And so this is what it's going to be. Each of those is going to be a time series. Each frequency component is going to be a time series. It changes with time, which captures the energy in that frequency at each instant of time. And so this is basically what we want to capture when we represent audio signals. So that's what a spectrogram is all about. Let's say I have a signal of this kind. Here's what we would do. We'd slice out a small portion of the signal and basically keep slicing out several portions. So these are segments of the signal. These are what we call windows. And from each window, typically they are 25 to 64 milliseconds wide, and the shift between adjacent segments is typically about 10 milliseconds. From each of them, they will compute. We like to taper the boundaries because you don't want edge effects. And then you compute a Fourier transform. And if you look at the magnitude of all of the Fourier components, that's going to give you a spectral characterization of the window. And you get one such characterization for every window, right? So you can keep, and if you plotted them all side by side, this is what it looks like. This is the spectrogram. This spectrogram is a visual characterization of the signal that went from here to my friend in China. The x-axis is time, the y-axis is frequency, and how many frequencies do I represent? If my analysis window has size L, then I know that I can have at most L/2 unique tuning forks. We've seen this, right? It's part of the restriction of sinusoidal decomposition. And so the number of rows in this matrix is going to be L/2 if I'm performing an L component Fourier transform. And so those L/2 components are going to go over all the frequencies in the signal. So this is actually showing the frequencies. And so at each point of time, the color shows the energy in that frequency at that instant of time. And it's converted the signal into a matrix, which is basically the signal bank of signals that went from me to my friend in China. So this would be a spectrogram. And so if I'm computing it, basically, I just begin by chopping each segment, compute the spectrum from it using the Fourier transform, and do that segment by segment till I compute the entire spectrogram. Very neat. I'm not sure who discovered this, but the spectrograms have been around. I'll stop right here. It's 3:15 rather than go around, right? But spectrograms have been around since before World War II. And so in World War II, we ran out of people. Everybody ran out of people. They were out there dying on the battlefields. But then you needed people to communicate. And so AT&T came up with this brilliant idea of employing deaf people to communicate. How do deaf people communicate? So they came up with this notion of visible speech. And this spectrogram over here, right? This, by the way, was a spectrogram, the picture that you saw for the Polish cup Polish, right? Computed exactly the same way that we just saw. But anyway, this spectrogram over here has this characteristic. This is speech. And you see these beautiful bands going up and down. They represent the resonances of your vocal tract. Your vocal tract roughly sort of shapes itself into many little resonant chambers. Each chamber has its own resonance. And the specific frequencies of resonance depend on the sound that you're trying to produce. And so you had there's a book called Visible Speech that you can still buy if it's available. It's been out of print for a while, but there are copies floating around, which was meant to teach people to read these things, to tell you what was being spoken. Because you can actually look at these patterns of resonances in the spectrogram and read what was said. Very impressive.
So
Yeah.
actually look at it and
Yeah.
know what the person was saying.
Yeah. And it's not hard. You can do it. You can intuit the physics of it. I mean, a simple thing like if I'm saying the sound I just have a relaxed vocal tract. So it's one long tube. It's a long tube. If the tube is long, what is the resonant frequency? It's going to be low, right? The wavelength is long. If I say E, I'm constricting my throat out here. So I'm separating my vocal tract into two sections of these lengths. So I will end up with two resonances, one for this and one for this. And both of them will be high because I've shortened the length of the tube. If I say something like ooh, I've closed my mouth. It's still a full tube, but now it's, the effective length is half of what I had when I was trying to say an ah. And so just by sort of visualizing the structure of the vocal tract, you can look at these patterns and know what was spoken or what was said. So anyway, I'll stop right here. I'll take any questions. And if there are none, we'll start looking at data-driven representations in the next class. Questions?
This is the short-time Fourier transform, right?
Pardon me?
It's like short-time Fourier transform.
This is the short-time Fourier transform. Indeed, it is. The short-time Fourier transform is just a bank of tuning forks. If there are no questions, thank you, everybody. Thanks for being here. I'll see you in the next class.